Okay, hi guys. Welcome to part 2 of partial fractions. Today I'll be just going through the second part because, like the last session we had, I went through the first part on. Now I want to continue with the final part, partial fractions, and then after this session we'll be doing trigonometric. Okay, let me check here. We'll be doing this part. Oh no, we did trigonometric substitution. We'll do trigonometric integrals here. Okay, so I'd like to welcome you again. The session took longer to start because my PC was acting up, but now it's fine. It's recording, and yeah, we are good to go. Okay, without further ado, let us just continue with our two other cases, then do some examples, some problems, and then yeah. Okay, so today we're doing part 2 of partial fraction. As I said, in the previous session, I gave you the two first cases, which is called the distinct linear factors and the repeated linear factors. Today I'll be giving you case 3, okay, which is the irreducible quadratics. Irreducible quadratics. Okay. Quadratics. Okay. So this is what happens, guys. Okay. If you are given an irreducible quadratic, okay, you are given a rational function of this nature. R at x all over q at x is equals to ax plus b all over ax1 squared plus bx1 plus c, okay? And then will be given by the other one, dx, oh no, cx plus d. Cx plus d all over ax2 squared plus bx2 plus c, okay? And then it will go on and on and on and on, okay? And then there's this final case, case 3, or case 4. This is case 3. So I've got the final case, case 4, which is called the repeated irreducible. So it's called repeated irreducible. Okay. Or quadratic. Quadratics. Okay. So in this case, we are given a rational function of some sort, r at x over q at x, given by two polynomials r at q. And then in this case, what we're going to have, it's a similar pattern, but now going to have a small or a slight difference, okay? So we're gonna have a and have, okay, let me say a1x squared. Okay, actually here, I shouldn't have put these ones with the thing. I should put one here, and one here, and one here. And here, I should put 2, only at the values, okay? Plus b1x plus c1, okay? Plus cx plus d all over a1 x squared plus b1 x plus c1, but this time it must be squared, plus da 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 da, okay? So in the last session, when we're doing our repeated linear factors, do you remember when we were doing our repeated linear factors, we had, okay, let me take an example, in fact, such that we can be able to see whether we are still on the same page or not, okay? But these are the main cases that we're going to be doing today, okay? And let me give you a little hint, or a little what do you call this? A little, I don't know what to call it, but it's a little something, which is nice. Okay. Okay, let me call it a tip, little tip. Okay. So this tip is, in most cases in the exams that I've seen, is they're going to give you the repeated irreducible quadratics. This is the most common used questioning when it comes to partial fractions. Okay. So yeah, it's fine. There's nothing much for us to do here. Okay. Now, I want you to look at the most important difference between the first part and the second part. The first part, we only wrote constants as our numerators. In this case, we are writing linear factors as our numerators, okay? So it is very important for you to understand the difference between the two. When we work with quadratics, we work with something like this. And then when we work with linear factors, we are working with constants as numerators, okay? But I'll show you. We're still going to do examples. Actually, let me take an example, which, no. Let me just take examples. I'll just see, okay? Let me see. The textbook. Okay, interesting. Okay, so let me wrap this out. Let us have our first example. I know you're not happy with the theory behind these things and stuff, but unfortunately, we have to do that. We have to do this theory because mathematics is governed by rules. So yeah. So the first example, let me just write here, example 1. And let me give you x to the power of x to the 4th all over x squared minus x plus 1, and then have okay, let me give you x squared plus 2 squared. Okay, now suppose they say to you write out the form of the partial fraction decomposition of the function, which is this function. Okay, so in this case, you are given this rational function, and they say to you they want you to write it in a decomposition, partial decomposition. Okay, so what's going to happen is they want you to write this thing in a form of ax plus b all over. In this case, you've got repetition because of this squared. Okay, so which means the first part is going to be something like this: a1 x plus x squared plus b1 x plus c1, and then the second part is going to be given by cx plus d all over a2 x squared plus b2x plus c2, and then there's going to be some other thing which we're going to write there, which is what comes after d or e, ex plus f all over a2 x squared plus b2x plus c2, but this time it's going to be squared. Okay, so we're going to write this in terms of whatever that I used to introduce the repeated irreducible quadratics. Okay, so in this case, it was easy because our denominator is already factored. Okay, and it's factored into 2 irreducible quadratics. We cannot simplify this any further. We cannot simplify this any further. Therefore, what we are going to do is the first part, we are going to give it this as our numerator, and then what is in the denominator is the first part of the factored irreducible quadratic. Okay, and then the second part is given by this, which is cx, not bx, which is cx plus d all over the first part, which is x squared plus 2. Okay, but since this thing is being repeated, we're going to have ex plus f all over the same thing, x squared plus 2, but this time it's going to be squared to show that this is repetition of this one. Okay, so this is the what do you call this? Partial fraction decomposition. Okay, this is the partial fraction decomposition. Okay, I don't expect you guys to to master this or understand this and say, okay, you guys know it, you are very well. I want you guys to be able to understand what we are trying to explain to you, that much theory and stuff like that, okay? So let me take an example which I did last time, okay? But are you fine with this idea so far, with this example? If you're not fine, please do let me know. Yeah, but if you're fine, we can continue. Are you well, guys? Which example did I take? Oh, yeah. I took it from the textbook. It was number 4. Okay. In the last session, I took this example, okay, which, let me call it example 2 in this case, which is x to the 4th minus 2x cubed plus x squared plus 2x minus 1, 2x minus 1, all over x squared minus 2x plus 1. Okay, so I said to you, we can rewrite this as x squared plus 2x minus 1 all over x squared, minus x squared minus 2x plus 1. Okay, you remember we rewrote this. This is where we left our solution. We said, no, this is where we should leave our solution for now. Okay, I want us to expand this a bit further. Okay, so I want us to expand x squared plus 2x minus 1 all over x squared minus 2x plus 1. Okay, so we're gonna expand this in terms of our solution. Okay, so if we have to find the partial fraction decomposition of this, we're gonna have to write this as x squared. Okay? But in this case, let me not write this as x squared. I'm more interested in this part. Okay, I'm more interested in this part. I want to understand how would you and I go about solving this part. Okay, so what's going to happen is, okay, let me write this one, x squared plus 2x minus 1. Do you see the bottom part? Is this bottom part irreducible, or can we reduce this part? What do you think, guys? Can I reduce this part, or it's irreducible? Meaning I can't simplify this any further. Can I factorize this part?
Yes, okay.
Okay. It's fine. So if I check x squared minus 2x plus 1, this is exactly factorizable as, let me see, 1 and 1 are the factors of 1, minus and minus. So this becomes x squared minus 2x plus 1. Okay, so this thing is factorizable. Oh, we can also write this as x minus 1 squared. Okay, so we can write this as x minus 1 squared. Okay, so in this case, you can see that this thing is a repeated factor, but is it a linear or a quadratic a linear factor? Is it linear or quadratic linear factor?
Linear.
Yes, I heard somebody was speaking. What were you saying?
Linear.
Is my volume that is down, or is it
Linear.
It's linear? Yes, thank you, my guy. Now what happens is, since it's linear, what we are going to use to denote this is x squared plus, in this case, we are going to just have an a all over x minus 1, which is the first part of this factorization, plus b all over x minus 1 squared. And this is what we denoted last time, which we called it a repeated, yeah, just what did I call repeated linear factors? Yeah. Linear factors. Okay. So most of the time, we are going to see something of this nature. We're going to see repeated linear factors most with our, what do we call this? repeated irreducible quadratics. Most of the time, they like to put them together. That's how the question will come. So yesterday, I was looking at a question paper from I want to show you. I want us to just read, and then we are going to see if whether my claims are true or not, okay? But this is how we can decompose this partial fraction into this particular form, okay? Are we fine with example 2? Okay, so what's going to happen is, let me take another example from the textbook. Let me take another example from the textbook, and let me name it example 3. Okay, let me name it example 3. Okay, so this is the one we just, actually it has 2 parts. Example 2 has got 2 parts. Let's do this one, okay? Let's do this one. The question is, it's x squared minus 1 divided by x cubed minus 3x squared plus 2x, okay? So we need to find the partial fraction decomposition. So okay, let us see the first thing that we can do from this, okay? In the denominator, I'm seeing a common factor, okay? I'm seeing a common factor. So at the numerator, we've got something like this, and the denominator, I've got an x, which is common throughout. So I'm left with x squared minus 3x plus a 2, okay? Now, the next thing that I'm seeing is, this thing is, okay, no way. I wrote the wrong thing, sorry guys. The bottom part here, because I'm seeing it here. It says x squared minus 1 all over 1 plus. Okay, let me just rub out this part. Let me just do it. All over x cubed plus x squared plus x. If I didn't see that thing, I was gonna give you a wrong question. It's this one, guys, okay? It's this one over here. Okay. Number 4b, which correlates to the one we just did now. Me, I wrote this part, the bottom part here. And I'm sorry about that, okay? Sorry about that. Okay, so I'm gonna have this x squared minus 1. I don't know what made me look at that. I really don't know. But hey, it saved us, okay? So here, we're going to have this part. Even here, we still got a common factor, which is x, and have x squared plus x plus 1, okay? Oh, now, if you can look at this one is irreducible, okay? This is an irreducible factor. It's irreducible. Irreducible factor. Because we cannot factorize this any longer, okay? So which means if we find something which is irreducible, then we can rewrite this and say, okay, we can write this as a over x, okay? Because x is the first factor, plus bx plus c all over x squared plus x plus 1, okay? So this becomes our final answer, okay? So let us check if this solution correlates to what we are supposed to find, okay? So let us check. It's 4b. It's number 4b. Where is it? This thing only shows odd number solution. So we only have 1, 3, 5, 7, 9, and everything. We do not have even number solutions, okay? So which means you are stuck with me with this one. This is my final answer. This is the answer I have. But it is true because this is how we should do it. This is how those rules told us we should do it. Yeah? So in this case, number 4, we can't find its solution, but yeah. So let me take number 5. Let me build your confidence. Let me take number 5. Do it as example 3. Okay. Let me take number 5 and do it as example number 3. Okay. So number 5 is this one. Okay. Is this one. So I'm going to do number 5. So number 5 says that we need to find the partial fraction decomposition of x to the 4th plus 1 all over x to the 5th plus 4x cubed. Okay. So in this case, I'm trying to build your confidence. Okay. Trying to build your confidence for us to see whether this thing does it work or not. Okay. So, oh, denominator also has a common factor with this one. X to the 4th plus 1 all over x cubed. This one is going to be interesting. Now we're going to have x squared plus 4. Okay. Now, do you guys agree that this one is an irreducible quadratic vector? Quadratic. Okay. This is an irreducible quadratic. Okay. And then what we know about that, what we call this rule is that we can rewrite this as a all over x. Okay. And then we're going to write this as b all over x squared. And we're going to write this as c all over x cubed, because this thing is repeated 3 times. Okay. This thing is repeated 3 times. Okay. And then we're going to have this other part here, which is going to be plus. Now, what comes after secant is d. Yeah. Dx plus e all over this irreducible quadratic. Okay. So this becomes our final answer. And then we can check it, because this one is number 5. And number 5 has got a solution. So let us check if this thing is true or not. Just to build our confidence. There it is. Our solution is true. Do you see? I've got this number 5 here. It says a over x plus b over x squared plus c over x cubed plus dx plus e all over x squared plus 4. Do you see the solution, guys? Okay. So this thing correlates exactly to the solution we found. Okay. Which it gives us confidence, because we believe now that whatever solution we did before is the correct solution. Okay. Is the correct solution. Now, let us go and continue. Number 6 is hard. I want number 6. Okay. So let me just expand and make even another example. Okay. Number 6. Hey, it's very interesting. I like it. I like it. Okay. So let us take number 6 as example 4. Okay. Number 6 as example 4. I'm going to take number 6, A and B. Okay. I'm going to take number 6, A and B. I'm using this textbook. It's James Stewart Calculus Metric version. Not metric version. It's edition number 8. Yeah, you can find it online. I also have posted it in the group ADBC. Okay. So we're using this text. So number 6A says that we've got t to the exponent 6 plus 1 all over t to the exponent 6 plus t to the exponent 3. I love such questions. Okay. Now, do you remember the rule that says that if and only if the degree of the numerator, which the numerator we used to call it Rx, is greater or equals to, now this is very important, greater or equals to the degree of the denominator, which is Q of X, then we are going to use the long division method. Now in this case, you see t to the 6 is equals to t to the 6. And therefore, we do not even want to stress ourselves. We go straight to the long division method. Okay. So according to the long division method, we're going to have t to the 6 plus t cubed. Okay. And then we're going to have this t to the 6 plus 1. Okay. This is the shortcut, guys. I don't like, okay, let me do this. According to long division, If we do not have any other reciprocals, we have to write it as 0t to the 5 plus 0t to the 4th plus 0t to the 3rd plus 0t squared plus 1. Okay, this is what is represented there. Okay, but me personally, I don't see why we should do that. Okay, because we know that these ones do not exist. So might as well just write this thing as t to the 6 plus 1. Okay, t to the 6 plus 1, because everything else is just 0. Okay, so I'm just going to write this as plus 1. Okay, so what's going to happen is I'm going to divide the 2. Okay, and when I divide the 2, I'm going to get the solution of 1. Okay, then I'm going to have 1 times this is just going to be t to the 6th, and then 1 times that, you're going to have t cubed. Okay, and then the rule said that we should subtract the 2. When we subtract the 2, we get this, and then we have that 0t cubed term. 0t cubed minus t cubed, it becomes negative t cubed, and then this one is just 0 here. So 1 plus 0, we are just saying that we bring this thing down. Okay, so now this term here becomes our function sx. You remember that function sx. Okay, so therefore we can rewrite this as t to the 6 plus 1 all over t to the 6 plus t cubed, as you remember it has to be sx plus px all over qx. And in this case, our px is given by whatever that is here, that is below the line. Okay, so our px is this thing. This is our px. So what is our sx? Our sx is 1 plus our px is given by negative t cubed plus 1 all over, what is our qx? Our qx is just t to the 6 plus t cubed. Okay, but we haven't solved the problem. We just found out what is this function in terms of using the long division, because we have got certain rules if we've got something like that. Okay, so now we are going to write the solution. We're going to have negative t cubed plus 1 all over t6 plus t cubed. Okay, now, okay, in the denominator, I can write this as, oh, there's something common in the denominator. So I'm going to have 1 plus negative t cubed plus 1. Denominator has got t cubed as a common factor. Then I've got t cubed plus 1. Okay. Multiplying the powers of the same base, we add the exponents. Okay. Multiplying the powers of the same base, we add the exponents. So t to the exponent, t cubed times t cubed is just t. Okay, let me write it down such that we do not lose each other. T cubed times t cubed is just t to the power 3 plus 3, which is t to the exponent 6. Okay, so multiplying the powers of the same base, we add the exponents. Okay, now we can factorize this. Okay, we can factorize this. This one is called the identity rule of cubic functions. Okay, so what we're gonna have here is 1 plus negative t cubed plus 1 all over. Now this becomes t cubed, and then we're gonna have t plus 1. So how we factorize this is we're going to have t squared minus t plus 1. This is how it goes. And if this thing was, okay, if this thing was t minus 1 cubed, we're gonna have t minus 1 and then have t squared plus t plus 1. It always goes like that. If this one is t plus 1 cubed, then what we're going to have is t plus 1, and then we are going to have t squared minus t plus 1. You must see how these two signs interchange. Only these two signs interchange. It's this sign and this sign. Here we've got a positive, and here we must have a negative. Only these two signs interchange, guys. Please make sure when you have given something of t plus something to the power or to the exponent cubed, you must always reply with this, okay? Or rewrite that, okay? So this will mean that now we are able to rewrite our solution. And this is going to be a very beautiful and Okay, so the first one is that we have got our t cubed, which means we're going to write this as a all over t. This is our first t. Repetition goes 3 times. B all over t squared, and then c all over t cubed. Then we have shown that we have repeated this thing 3 times. Then we're going to have our second part, which is going to be d all over t plus 1, which is this one. And it's also linear. When it's linear, we always use what? A constant in the numerator. Plus, what comes after ex plus f all over t squared minus t plus 1. Then this becomes your final answer. Okay, so this becomes your final answer. Unfortunately, number 6, we can't see its solution, but I am 100% confident that this is true. I'm 100% confident. Okay. Do you have any questions? I've been talking. Do you have any questions, guys?
No.
Okay, thank you, my guy. Okay, so, I always say there are many ways to kill a cat and there are many cats to kill the man. Let me try and see if whether we can't find any other solution. Okay. I mean, we can't find any other way to find the same solution. Let me just wrap up this part and this part, and let me leave the final answer. Okay, now we're gonna use mathematical manipulation. I'm going to manipulate